Thank you for the introduction. So the plan for today is I want to talk to you about graphs in the context of descriptive or Borel combinatorics. So to do that, I want to motivate some things by just referring to some really old theorems by particularly one theorem by Cantor. And I don't want to spend too much time on the proof because I think either you will remember the proof and then the quick reminder will be clear, or you don't remember the proof, in which case a short explanation is probably not enough anyway. So this is like a classical proof in set theory, right? So maybe let's just fix a few things. So for this talk, X is a Polish space. Right, so it's separable, completely metrizable topological space. And common examples are, of course, the reals or the Baire space, which is all sequences of natural numbers with the product topology, or just the binary sequences, and so on. I think these are all the examples that I will actually need. Okay, so there's this theorem usually attributed to Cantor. I don't know the year, but it's a long time ago. So the idea is that closed subsets of, let's say the Baire space, right? Omega to omega cannot be counterexamples to the continuum hypothesis, right? So if F is closed, then either one thing happens, and that is that F is countable. Let me just use omega. Or there is a continuous embedding from the Cantor space to F, right? So there exists C from 2 to the n F continuous and injective, of course. Right? Actually, let's call this pi. Okay. So there are two proofs that people usually go through to show this. But when you're developing the whole theory of descriptive set theory, this becomes either evident or there's not too much to mention here. But I just quickly want to make a quick distinction between two ideas that can be used to prove this very well-known theorem, right? So there's one proof that uses the idea of derivatives. This is a little bit subjective, like the proofs are very similar to each other, and the distinction will only be relevant for what I want to do afterwards. But just indulge me with this short argument, right? So the idea for the proofs with derivatives is that you take some tree whose body is F, right? Because closed sets are characterized by that. And then I iteratively remove nodes that don't split in the tree anymore. And by the time I'm done doing that, eventually this sequence will stabilize. So either I have enough things that still split to find an embedding of the Cantor set, right? If everything eventually splits, well, I can just adjust the binary tree so that it fits inside my set F. Or if I can't do that and I don't have enough splitting nodes and I get to this point after just countably many steps, then you can show that F has to be countable, right? But the idea is that there's this like a derivative iteration. Now there's another proof that is a bit shorter, although I will argue is in this case it's kind of maybe trivial to make this distinction. So this is something that I call the condensation points. I don't know if there's like a better name for this. So a proof by condensation involves defining like the kernel, the core, I don't know what the name is, directly, right? So you simply say you take in whatever tree corresponds to F, you take those nodes that have uncountably many extensions in the tree. And then there's two possibilities, right? Either this will be empty, in which case no node has uncountably many extensions, and you can argue that F again has to be countable. Or it is not empty, in which case this is already the perfect set that you're trying to find, right? So it's a tree where everything has enough extensions so that you can continue the proof. I know I'm skipping over a lot of details, but this isn't really that important. Just there's two ways of doing this, right? This one doesn't require any iterative movement. You immediately get this. Okay. Now, why bother making this distinction? So I haven't really worked on this with a lot of detail, but the step where this is empty, showing that the tree, sorry, that F is countable requires some sort of axiom of choice, right? And so people interested in generalizing this in the projective hierarchy might prefer the first proof over the second, even though it looks a bit longer. But I'm not interested in that, at least not yet. So I prefer the shorter proof. Okay, so what I want to do is I want to look at that theorem, maybe ignoring the proof for now, and I want to give a version of that in graphs. So let me tell you a little bit about graphs. So a graph on X is an irreflexive symmetric relation on X. In other words, I'm not really distinguishing between G and what people usually call the set of edges of G, right? So G is the set of edges. It's pairs of elements of the space X, which are the vertices. Irreflexive means that I'm not allowed to connect a node to itself. And symmetric means I don't really care about the order, right? The edges don't have any sort of direction, which is usually drawn like an arrow. People call that a directed graph. I just care about undirected graphs, I guess, right? Now, some imposition on this, since we're talking about, topological spaces, I do want G to have a sort of low complexity that I can refer to. Otherwise, there's not the theory I want to work with doesn't quite work out. So from now on, G will always be analytic. Right? So analytic, for me, the definition can just be the projection of where else it's, or rather, there is a pi from some Polish space E into G, right? Polish. And I guess I could pick this to be the bare space or something, but for my purposes, I don't really care what the space is. Okay, so what would be a natural version of Cantor's theorem in the case of this? For that, I have to define one more thing. So the coloring, let's write this as a proper definition. So a coloring is a mapping. Let's call this C. From the vertices of G into typically people pick a polar space or something with a little bit more structure. I don't really care about the structure of the colors right now, since I will only distinguish uncountable from countable. I don't want to be any more specific than that, or just finite numbers. Right, so it's a mapping such that adjacent vertices in G get a different color, right? So if X and Y are G, then the color of X is different from the color of Y, right? And why do I care about this? Well, the chromatic number of G is the least number of colors that I need for there to be some coloring, right? I guess sometimes this is called a proper coloring, but that's the only type of coloring I'm interested in. The least for which there's a coloring. Right? So if I have colors, actually, I could maybe write down a very simple example. I know this isn't graph theory, but it will become relevant in a second. So here's a really simple example. So take the space as the Cantor set, right? All binary infinite sequences of zeros and ones, and define a graph where two of these sequences are adjacent if they differ by 1 bit, right? By saying x and y are in G if they differ in one bit or one digit, whatever, right? In precisely one bit. And then what are like the finite approximations of this? Well, the easiest one is if I just take, sequences of length 1, then I can also take sequences of length 2, right? So something like this, right? And the next one will be like a cube, right? So these are finite approximations, but of course the resulting has infinite chains. So hopefully it's not too hard to convince yourself that all of these are two colorable, right? You can just alternate the colors and explicitly define a coloring based on the parity of the number of ones in each sequence, right? Okay. Anyway, something like that, right? And so the chromatic number of G is actually 2, as all of the finite approximations are as well. This requires maybe a little bit more work than what I just said, but there's this theorem called Erdős-de Bruijn, which would easily justify that, or some sort of compactness argument would yield that. Now the problem with that is that this coloring isn't explicit at all. And if you think about it, it's not too hard to see why, right? So in the finite case, the coloring has to be some sort of parity function, right? It has to decide whether there's an even number or an odd number of ones. So in the infinite case, something similar must happen. But for that to work, you kind of have to invoke the axiom of choice, right? To pick a representative in each connected component. Because G is not connected, even though these are all connected. So maybe we want to impose some more conditions on the coloring, namely that it is definable in some way. So I will actually prove that you cannot define a coloring for this, because essentially that core idea for the proof is what will give me the theorem that I'm actually interested in presenting. So, okay, so the next definition, if we only allow definable colorings, and in this context, let's just say Borel colorings, we get an analogous notion of the Borel chromatic number, right? So some common properties, some of which I will actually use, is that, of course, if you have a Borel coloring, then you have some coloring, right? So the chromatic number of any graph is bounded by the Borel one. But it might be the case that the Borel chromatic number increases because you are forced to use more colors when you want the colors to be somewhat definable, right? It's an additional restriction. Another one that's not trivial to prove, but it is proved in the very first paper that, as far as I know, developed this theory, which is by Kekris, Zaleski, and Todorovic, 1999, Borel chromatic numbers. I'm not going to write down the reference, but so if all vertices have degree, the degree is the number of neighbors, right? Have degree less than k plus 1, sorry, less than k, then something that is true for finite graphs happens to also be true for the Borel chromatic number, which is that you can bound the Borel chromatic number by k plus 1, right? This is not hard to see in the case of finite graphs. In the Borel case, it takes a little bit more work, but it is also true, right? So maybe I can just add the reference. So this is Kagris-Zaleski, Todorchevich, 1999, and they define these things for the first time, and there's plenty of examples. Now I do need to prove to use something about that coloring doesn't work. That coloring is not a Borel coloring, but to do that, I will need to invoke a little bit of other stuff. Let's see. The Borel chromatic number should have given this thing a name, right? So let's call this C, I guess, right? Like the Cantor graph or something. Okay, so I claim that this graph has uncountable Borel chromatic number. So that's interesting, right? Because this is like the biggest jump that you could get. You have a graph that's has chromatic number 2, but if you want the extra restriction that the colorings are definable in some sense, even just bare measurable, then the chromatic number jumps like crazy, right? Not even incountably infinite many colors are enough to color that graph. So in a way, this is like the worst thing that could happen, because essentially you need as many colors as you have vertices. So you might as well just give each vertex a unique color, which is like the most trivial coloring. Okay, so this I will use this theorem and that theorem, connect those two ideas, and give you a new theorem. Okay, so how do you prove this? So suppose that I somehow manage to split the space of vertices, which is actually the Cantor space, right? So the Cantor space, I split it into countably many pieces, right? Then by bare category arguments, not all the pieces can be meager, right? Can be topologically small, because if they all are, well, the union is meager, and then then everything is meager, right? So by bare category arguments, there is some n such that Cn is, well, not meager, but not meager doesn't mean, like, if it's topologically not small, it doesn't mean it's topologically large, but it is if you zoom in enough, if that makes sense, right? So there is a T such that Cn is actually co-meager in the basic open set. The basic open set given by T, which is simply all extensions inside the Cantor set, right? Right, that extend T, right? So that's the idea. All you need for this to be true is that these are somehow bare measurable, or Borel measurable is stronger than that, so it definitely works, right? Then define a function, yeah, let's just call it f, from this subspace in which this is co-meager to itself, where you flip one digit at a time, right? Actually, sorry, just one digit. So you take something that is, T, extend it to something, and then something else. This is concatenation, right? The frown symbol. And then what you do is you flip it, right? You flip this bit, and this is a homeomorphism, right? Because you're just changing finitely many things about it. So it's a homeomorphism. And as such, it preserves the topological properties, right? So this co-meager set here still has to be co-meager when I apply f to it. So I have this co-meager set, and I have this other co-meager set, the image. So the intersection is still co-meager. So this is co-meager. Maybe I need to intersect this with one of these things, but I think this is fine. Co-meager in T, right? And I'm done. Why am I done? So this is problematic, right? Because if this is co-meager, then at least it's not empty, right? So there's something in here. But every time I flip a bit, I create an edge, because that's how the edges are defined in C, right? So this creates an edge inside every non-meager set of the sort. But then Cn cannot be a chromatic class, right? Because they can't have the same color if there's an edge, right? So Cn has an edge. Has an edge. So it cannot be a chromatic class. Now we will see that this sort of trick works in a much more general sense. So here's a theorem that I need to mention by the same people that I cited, so Kekris, Lesk, Georgievich, 1999. And they say that if you try to abstract the property that works to basically complete this proof, if you think about it, all I need is T to be somehow dense in my space, right? Maybe I don't need to be able to find any T. I just need to, be able to find some T after which flipping still stays inside the same graph. So I know I'm skipping. I'm not going to construct this graph, but there exists a graph which is called G0. But the point of this example is that G0 is actually a subgraph of what I just defined, right? It's a subgraph. It is Borel, but it has the property that kind of resembles the Cantor theorem, right? So for any G analytic, the following is true. Either the Borel chromatic number of G is countable, right? Exactly like I wrote there, or there exists, let's call it F. I should have called that one F2. Well, there's a function from G0 to G that is both continuous and a homomorphism, right? It preserves the adjacencies. Right. Okay. So the idea is that in the original paper, yes. All right. Okay. Okay. So why can I ask this F to be injective? Right. So that's a good question. So in general, the answer is no. You cannot make F injective, but you can make it injective if you restrict the class of G a little bit further. If you ask for G to be locally countable, then you can find an injective function, but not in general. However, I should point out that the natural analog of this is the homomorphism, right? Because Cantor's theorem is a theorem about cardinality, right? It's about counting how many elements you have. So the first property says you have small cardinality, or you have a function that witnesses the large cardinality in some strong sense. So what function preserves cardinality? Well, that's injective functions, right? But here this is about the chromatic number. So what functions preserve the chromatic number? Well, that's the homomorphisms, right? Because this gives a lower bound on the possible Borel chromatic number of G. Namely, it has to be at least the one of G0, which I haven't really written down, but if you believe me, is also uncountable, right? Because that's the whole point of this. Right. Okay, so the original proof that you find in the paper uses effective descriptive set theory. And later, Ben Miller, found a classical proof. And the proof somewhat looks like the derivative version of Cantor's theorem, using derivatives in a way, right? So it resembles the original proof of Cantor's theorem. I should say that this is a lot more complicated, right? Because the way you connect these two is if you take the complete graph, basically, right? The complete graph would give you a version of Cantor's theorem, and this generalizes that in that sense. But if the graphs are not complete, well, this can be a lot more complicated, right? Okay, so Miller found a proof using derivatives, and I think he also mentioned that there is a proof using the condensation idea, and claimed, or let's say hinted, I don't know what's the right word, and yeah, presented. Okay, let's just say, and with Anton Bernstein presented a proof with the condensation paradigm. This isn't very formal, by the way. It's just, if you look at the proofs, one seems to resemble the other one more than the other, right? Anyway, okay, so what did I do? I looked at a version of this where you change this number and get a different dichotomy, and the proof that is known of that uses derivatives. So what I did is I just rewrote it using condensation, and it's a lot shorter. Right? So let's dive into that. Okay, I think we're right on schedule. Okay, so here's a theorem. This is, I think, 2021 by Caroy and other authors, including Ben Miller, by the way. I think this is 2021, maybe published a little bit afterwards. Okay, so there exists an L0 Borel graph such that for every G analytic, we get the same conclusion essentially, but now we want to distinguish between two other types of chromatic numbers. This one distinguishes, did I read this correctly? Yeah, the countable from the uncountable, the same way that Cantor's theorem works. This one will distinguish the Borel number 2 from Borel chromatic number bigger than 2, right? So either your graph has Borel chromatic number 2 or less, yeah, or there is a function f from L0 to G that is continuous and homomorphism as well. Right? Now you might be wondering what happens between 2 and omega, right? There's a lot of numbers that you can ask whether there is a dichotomy there. And that's even more recent work, I think, by Todorochevich and Vidyansky. And they basically disproved all cases between 3 and omega, right? So there is no other dichotomy, at least as general as this one, between those two in the way that it's written.
What is the right number of cells?
3. Yeah. Okay, so let's try to prove this theorem. So let's construct. Actually, let me just change one thing. Let me just add a line here. Because why not? Let's construct L0, and that will probably take the rest of the talk. Yeah. Yes, I do know what's special about 2 and not 3. So okay, so here's one explanation that does make sense, but let me just say this. In the case of finite graphs, to distinguish to decide whether a graph is two colorable or not is very easy. All you do is pick a point, alternate colors. If that works, well, then it works. And if it doesn't work, then there's no other way to do it, right? So it's you can solve that in polynomial time, essentially. So it has a lower complexity. But to decide whether something is three colorable or not, that is NP complete. So it is as complicated as deciding any other NP complete thing, right? And that's more or less the reason behind this, right? So there's some even more recent work by Riley Thornton, where he connects those two ideas more precisely, whether something is a constraint satisfaction problem has an NP complete decision problem, and whether or not you can find some sort of analog dichotomy in this. So that's more or less the reason. So deciding whether something is 2 Borel, or sorry, 2 has chromatic number 2 or not is easy compared to the other numbers. This is not a complete explanation because there are some things that in the countable case become easy to decide, right? And that's why you can get a theorem like that. So it's I know it's not a complete explanation, but that's more or less, that's one way to look at this, right? Okay, so let's construct L0. All right. Okay, so this will be a little bit annoying, but I will fix a parameter from now on. And this parameter will be an index for a type of graph that looks very similar to L0. And in the end, I will tell you how to get rid of the parameter, right? So I'll tell you why I need this parameter in a second. So you fix a real number, or just maybe I should write it like this. Fix a sequence. You know what? Let's just, so let's see. Okay, I want a sequence of natural numbers that only takes odd values, right? Yeah, that's the only type of function I will care about, right? So the image of this just consists of odd values, right? Odd numbers. So let's just write it like that. Okay, so we will construct. The trick is you construct finite approximations of L0, and then I show you how to find those finite approximations in a finer and finer way inside a graph G, where G has Borel chromatic number 3 or more. And that's how you essentially conclude the proof, right? So let's, yeah, there's a lot of setup to this. Let's just construct a family of graphs. They all have this pesky parameter C, but let's just, yeah. Right, so what do I want from these graphs? So first, LNC is a finite path. So all of these are finite, finite graph, finite paths. The second property is that this has endpoints that are labeled in a particular way. This is just so that I can refer to them later. And the way that they are labeled is with this sort of index. Okay, you know what? I should do this because otherwise it'll become more confusing. So before I fix this, let's just fix an infinite path from which we're going to take edges, right? So let's just fix a path or array, if you will. Right, so I will just take the P, what should I call this? P0, P1, P2, right? So this is just an infinite path. I could assume that these are just natural numbers, but the labeling gets very cumbersome in anyway. So calling them P will help me keep track of which ones come from this path and which ones come from some other path. So you'll see why this makes sense in a second. So the endpoints of this finite path are labeled as follows. So they're basically labeled as P0, followed by n minus 1 zeros, and then I. Right? It's a path, right? So there's two endpoints. So this is 1 and the other with 0 and 1, right? So that's how I label the endpoints. And what other property will I actually need to cite from this? I think that's probably it. Okay, so this one's probably not too important, but every vertex of LNC has the form PK, and you extend it with some t of at most length n, right? So t is some binary sequence of at most length n. Okay, this is a bit abstract, but there's actually a concrete way to look at these paths, right? So how do you construct the paths. Yeah, let's do that here. So the trick that what I want to do is whenever I replicate this argument, where using bare category arguments, you create an edge which contradicts something, right? I want to do that, but instead of creating an edge, I want to create an odd path, because having an odd path between two similar vertices is what is going to ruin the true colorability of the graph, right? Because you cannot color the endpoints of an odd path the same way if you only have two colors, if that makes sense. Okay, right. So L0C is simply the path that consists of P0 until C0. That makes sense. So this is just a path. And then what I will do is I will grab two previously constructed paths, LNC and LNC, and I will recursively construct LN plus 1C, right? So given LNC, we construct LN plus 1C as follows. So you take the two copies, and then you find the correct endpoint, and then you connect those with a path of length Cn, right? Cn, the parameter C, is simply encoding the length of the path that you need at each stage, right? So you connect them, you connect the copies of, and I have to pick the right endpoint because they have to be the same endpoint in both copies, otherwise this will not work at all. So let me see, the endpoints are the EIs, right? So I think it works if I do this. So the E1, it doesn't matter, right? It's just a number anyway. By a path of length Cn, right? So this is an odd number, and you connect those. So you have to take P0, P1, PCN, right? So you take this path, and then you connect these to the endpoints E1 and E1, right? Now, if we want to do this formally, we need a way to distinguish these two copies, right? We can't just take the union. So what we do is, to the ones on the left, we append a 0, and to the ones to the right, you append a 1, just to distinguish them, right? So maybe just to do this a little bit more formally, for every vertex in L and C, you append VI to Ln plus 1C, and you then you still need to append the path, right? So you then append the path that I just described. So P0 all the way to PCN, and that's it. The edges are given by the obvious way, right? You just, yeah. Okay, so this is how you recursively construct. Now here's an important remark, and some people will criticize this, but I feel like I can justify why I did this way. You don't really need to know all values of C to construct the first n finite paths, right? Think about it. To construct Ln plus 1 from Ln, all you really need to know is the value of Cn, because that tells you the length of the path, right? And if you think about it even more, so C is basically saving, keeping track of the lengths of all the paths that I have so far. But I don't need, for example, the value of C in C at n plus 1. The reason I do it this way is because otherwise I have to include way more notation and be like, okay, this is restricted to something and then expand it. Anyway, this might cause confusion later, but I will die on the hill that this is better this way. Maybe not. We only need knowledge of C restricted to n plus 1, I guess. Actually, let me just keep it like this. To construct up to ln C, right? You only need the first n values of C, and then you can construct the first n values.
So what's the reason for this bizarre labeling that you have in here?
So when I define the actual LC, I will need to refer to the points in each copy individually. And for that, I need to keep track of exactly how they are behaving, right? So if you consider the sequence of graphs, where did I write it? I mean, just the sequence of all of these graphs, what determines a node? You need to know several things in this construction, right? You need to know in which position of a path was it added, and then in which side is it being copied to, right? So you need several parameters to fully describe where the points are. Yeah, I tried simplifying this, but I think there's no way to actually define the big graph LC without doing this.
Forget what the underlying sets of the LNCs are, and just name the embeddings between them. Right, between LNC and LN plus 1C, you just have two embeddings. You have an embedding to the left, an embedding to the right. And then your graph consists of a path vertex followed by a sequence of 0, 1 choices where you choose how you embed into the higher graphs.
Okay, so
this completely avoids this bizarre labeling that you have over here.
so that I think that would work. Maybe there's a way to write it, but it's also important that I need to keep track of at what stage was a vertex added. So it's not enough to just know the position and the copy. I need to know like the age of the node, right? So for example, those nodes that just got added in this copy, I have to distinguish them from the ones that were added like 3 stages ago. So that does require 3 parameters somehow.
That's just enough that the underlying sets of all the graphs are just.
I see, but I don't know if it's that clear to glue them together then, if they're coming from different sets. Maybe there's a different way of describing this in a shorter way. Okay. Okay, so here are some basic properties about these graphs that I will need to refer to later. Okay. But before that, here's a quick definition, right? So given n positive, I define of LNCG as the set of all phi's, where phi will be simply a function from the vertices of Ln to the vertices of G, right? So this is like a finite approximation of Ln inside G. X is the vertex set, right, of G. Okay. So we say, so this is a polar space in its own right? It's a closed subset of some product space of this. So this is a polar space. I can talk about the next things here. So we say a subset of these elements are called copies. By the way, you can call them copies because it's like a copy of LNC inside X, right? Okay, I'm missing something important. So I don't just want the copies to talk about the vertices. I want them to also talk about the edges. right? So this mapping, I can think of this mapping as, I want to use the same letter, even though, formally it might not be the same function. So this one will take on nodes. Actually, yeah, let me write this. Vertices, and the other one will take on edges. Right. So this one will also take the edges of L and C to X. Let me just check if I actually want the real edges or the edges of the polar space. Doesn't really matter right now. Okay, no, I do want the polar space. Okay, so this is the polar space of edges of the graph, right? It's the one that you project onto G to get G as an analytic graph. Okay, so for a subset of this thing, Borel, right? For a Borel subset, you can define the following, right? If you have a set of copies of a graph, then you can look at pieces of those copies, right? So for example, if you take a vertex V, vertex inside LNC, then this is simply the set of all copies evaluated at this point, right? V in, sorry, phi inside L. And similarly, you can define something for the edges, right? So if you have an edge UV, then all you have to do is take these, which are also defined by this, right? Phi of L, right? So you have a finite set, a finite LNC, and then you look at all the copies that you could find of that graph inside the graph G, and you take some subset of that. And then you pick a vertex, maybe one of the endpoints, and then you look inside those copies, what are all the endpoints that are being, labeled by this. Right, so we say L is tiny, is a tiny set if it has the following property. If there exists a K such that all odd paths with endpoints in L, and now I get to pick whatever vertex I want, right? Because I don't want to pick any vertex. I just want the vertex that will actually continue the construction. And if I go back, the vertex that I care about it's one of the endpoints, right? I forget which one. I guess it's E1N, right? That's the one I want to connect. So I look at the copies of E1N, and all odd paths with endpoints have a length, have a uniformly bounded length, right? So 2 to the k minus 1. So if that happens, I call this set tiny. Now I'll explain where this definition comes from in a second, because this is basically the idea that connects the the countable argument with the argument for just two colors. Okay, so L is large or small. Is the countable union of tiny sets. And this defines a sort of sigma ideal, right? L is large if it isn't small. Isn't small. Now let me briefly tell you how these two things are connected. Just erase this. So why would someone come up with that weird definition of tininess? Well, first, there were a lot of iterations that this proof went through. And that's the one that seems to work. But here's a better reason, actually. So here's a sort of technical lemma, right? Okay. So this definition here makes sense for any graph, right? For any finite graph, you can ask yourself, what are the copies of that finite graph inside G? So you could define this not just for graphs of this type, which makes this actually a little bit less elegant if you think about it, but you could define this for arbitrary finite graphs. And in that context, if your finite graph consists of just a point, then this set is just the vertices of G, right? What are the copies of a point in G? Well, that's everything, right? Every vertex of G. And in that context, so if we identify, or rather, let me write it like this. So let's identify V of G with the copies of, just a point inside G, then I can still make sense of what it means for this set to be large, right? It's just that definition applied, and the endpoint would just be the only point, right? Something like that. So the reason that this weird thing happens is that so if I'm trying to say, if the chromatic number, the Borel chromatic number of G is actually the other way around. It's the other way around. I mean, just a contrapositive, right? So if V is small, then the Borel chromatic number of G is at most 2, right? This isn't obvious, but it requires some technical steps. I can address this later once we actually get to the construction, if there's time. All right. So what were we doing? All right. Okay, let's continue proving some important properties of this. What I want to do is I've already imposed a sort of largeness property on copies of my graphs, right? I want to do this because I want to find larger and larger copies of these graphs inside G. And to do that, to be able to continue the construction, I need this flexibility that if you have many copies, then at least one of them must be able to continue with the recursion, right? If I have many copies of LNC, then surely with these properties I can find a copy of Ln plus 1 C. That's that's sort of yeah, I know. That's sort of what I want to do now, right? Okay, so let's try doing that. So here's one more definition. How do I talk about the copies of the next stage of my finite graphs in terms of the previous stage? I need a way to talk about that, right? So the way you talk about that is that you say, so let phi be some copy of Ln plus 1C in G, right? And then, well, this is, talking about copies of Ln plus 1, so, the graph Ln plus 1. So where did I write this? Recall that almost all the vertices of Ln plus 1 look like pk and something appended to it, right? T might be of length 0, but that only happens for the path that I'm connecting right now. The vertices that are inside the copies must have at least length 2, because I already appended a 0 or a 1 to them, right? Yeah, the notation isn't the most friendly. Okay, so for a vertex in LNC, we define the following. So phi of I of Vi, actually I think I want the opposite of this. Wait, is phi I the copy of the small one or the large one? Okay, so phi I is the copy of the small one. Right, that makes more sense. So phi I of a vertex inside Ln will simply be, you ask the larger set, what do you think that vertex should be inside G? And then the answer is this, right? So phi I is simply pointing to the left or right copy, and this is telling you, what that vertex is. Yeah, I think maybe it isn't necessary to do this notation, but I don't really see a way to simplify this much more. Okay. So given definition 1 and definition 2. So now I want to talk about the copies of the large graph, right? So given an L inside LNCG, how do I talk about the copies of the larger graph, but that are somehow compatible with the smaller one, right? Because these are all just paths. So of course you can find a bunch of paths, but if I want to iterate this and make these things to be topologically compatible, I do want to talk about the smaller copies that I'm referring to in the path, right? It's not just any path that I want. So given this, define L plus C. This will simply be the set of all copies of the larger graph that are compatible with the smaller copies, right? So compatible simply means that phi I is inside the smaller one for both I, right? Does that make sense? So you take the copies of the larger graph that are compatible in the sense that they are actually pointing to the correct node inside the smaller graph, right? You have this compatibility. If L is Borel, then so is L plus C. I don't want to get too hung up on those things, but if L is Borel, then LV might not be Borel, but this is analytic, right? So there's still we can still work with that. Okay, so I think I can erase this. So here's a crucial part. This is the most important part of the proof, because if you understand this part, then the rest is really just replicating one of the proofs that I already did. So the most important part of the proof is showing that I can continue recursively constructing the finite approximations of LC. I haven't even told you what LC is yet, but we'll get there in a second. Yeah. Okay. So here's a proposition. So the first property doesn't even talk about what I just defined, but let's just say this. If you take two vertices that come from the same position in the copies, and you look at them in the larger copy, so in Ln plus 1, they are always an odd distance apart. That's kind of obvious, right, from the construction. So given V in, actually, yeah, this is fine. I should have, that's the vertices of Ln. I hope that's clear. The vertices of LNC, if you add an I or a 0, sorry, a 0 or a 1, those two are an odd distance apart in the larger graph, right? Are an odd distance apart in Ln plus 1 C, right? That is just, I mean, that's not hard to see, right? How do you get from one vertex to the other? Well, you first get to the endpoint, because that's where the bridge like crosses, right? But the bridge is always an odd distance, right? So you have two lengths that are the same, and then you cross, so that's always an odd number, right? So this isn't too hard to see, but this is the reason why the limit of these things will have Borel chromatic number 3, right? I guess at least 3. You'll get Borel chromatic number at most 3 because of the thing that I think I already erased, right? That all the vertices have degree at most 2. So the Borel chromatic number is at most 3, based on one of the properties that I think I already erased it. Anyway. Okay, so the second property, and this is the most important part of the entire proof. The rest is just guiding the construction using this idea. If L home LNC is a large Borel set, if you have a large number of copies, a large amount of copies of Ln, we can continue the construction. But here's the problem, and this took me a long time to figure out. But so the problem is that I cannot just add any path that I want, right? Because you'll see why in a second. Maybe should I write the wrong thing and then correct it, or I'll just do the right thing and whatever. Then there is a D. So maybe you have to change the parameter. This is where it gets kind of tricky, because in the original proof of G0, sorry, not the original, the proof of G0 using the condensation idea, you don't have to worry about this at all, because all you're doing is adding edges. I know you don't know what I'm talking about. I'm just about this because I didn't explain what G0 is, right? The problem here is that the paths vary in length, so you have to like dynamically update the parameter as you're going through the recursion. And this, like I said, this took me a while to figure out, but I think it works. And this is the point where this might be a bit disfavorable. That's not a word. Okay, let's just continue. So C and they coincide up to the stage, but now I have to maybe switch the length of the path that I'm adding, right? So there is one of these such that L plus D is large. I mean, I want to conclude large, but first let's show something slightly easier than large, namely that is non-empty, right? And maybe then I can show that it's large. So if L, let's see, is large Borel set, there is a D with the same properties, right? With the large in whatever home, C, N, D, all those things match. Now, something that I want to point out, I have all these nice colors, maybe I can use this one. This implies that LNC is actually the same as LND, right? Because they don't distinguish each other up until the stage where you need to know the value of N, right? So that's the new path. Okay, so let's prove some of these things. So I think the first one was clear from the hand wavy explanation. I need more space. Yeah, let's prove here. Okay, so let's prove number 2. You'll see that number 2 is easy, and number 3 will follow from number 2, but that's the one that was maybe a bit trickier. Okay, so number 2 is as follows. So since L is a large Borel set, well, surely it's not tiny, right? It makes sense, by the way, that to prove something much weaker than largeness, namely that it's not empty, you need something much weaker than, well, largeness, namely that it's not small. So yeah, maybe that's a better way of writing this. Anyway, since L is not tiny, that means that L, E, the endpoint, whatever endpoint is the right endpoint, E1N, doesn't have that property that defines tiny, right? And the property says that the odd paths with endpoints there are uniformly bounded. And here you can see why I need a different parameter, right? Because the negation of that doesn't tell you what the length of the path is going to be. It just tells you can find a path that is as long as you want, but it might be much longer than what C allows. So this means there is an odd path connecting two points, and I can make this as large as I want, but not exactly not give it an exact length. So let's just make this larger than 2n minus 1 for reasons that this is not important. This is not too important for the proof. But if I can make it as large as I want, I might as well pick a parameter and make it larger than that one, right? Right, so there's a path of length k, and now I have to update the parameter c for this with this k, right? So define d of n as k, which might be bigger than c of n, right? And such that cn, you can just give it the other value of c, and whatever happens afterwards doesn't really matter, because so far we are not talking about anything bigger, right? But you can make d match c everywhere except there if you want it. Anyway, okay, so there's a lot of formal steps here that I'm skipping, but the idea is simple, right? You found a set of copies of these endpoints, and I've concluded that at least two of them are connected by a large, like a long odd path. So you take those, and now you have constructed a copy of the next path, right? So this constructs or produces, I guess this constructs a copy phi of this new graph ln plus 1 d g. And so far that's what I wanted, because this copy is compatible with the previous ones, right? I'm just joining two points, so this works out, and at least I have proven that this is non-empty, right? So now comes the slightly trickier part. Okay, now I want to show that it is actually large. I can find a large copy of the next stage. You'll see why this is useful, right? Because I want to do this over and over again. I want to keep finding large sets of the larger and larger approximations, so that basically my recursion doesn't stop until I'm all the way until I found the limit of whatever these graphs become, right, in the limit. So let's do 3, and we'll barely have time to to explain how this is useful. So 3 is done by contradiction. So suppose this is probably the one spot where people are going to criticize my choice for the notation d, because you'll see in a bit. So let's suppose that it doesn't happen, right? I'm assuming that L is large, but there is no way to extend C in this form that will produce a large set, right? So suppose that for all D that that basically just extend C in one point in N, that is not large. And not large means that you can decompose it as a countable collection of tiny sets. Now this is the problem. These sets are all tiny, but they are tiny in different ways. They're tiny in different spaces because they depend on that pesky parameter. So we have to do something to fix that, right? So all of these sets are tiny, but they are tiny where? They are tiny in this set right here, right? Ln plus 1 for D, but D is changing, right? There's a different D that's being parameterized here. So that's how do we fix that, right? Well, we fix that by going one level down and using this property. Basically, you go one level down where they all agree, and then they can only disagree in countably many spots one level higher. Okay, so let's just invoke the definition. So by definition of tininess, what does it mean? It means that fmd, if I pick the right endpoint here, which I am afraid of getting wrong. Let me see what that is. The endpoint is just this one. Okay. Okay, that works. So all of these are tiny, right? All of these are tiny by definition. Okay, actually, like I said, this is the tricky part. All right. Okay, so you have this property about the endpoints of all odd paths connecting these sorts of points is uniformly bounded, right? Uniformly bounded by something that depends on M, basically. M and D. So now, okay, so you consider, like I said, you have to go one level below this, right? So you consider H, where I pick out the copies of those endpoints. So E1N, where phi is in L, the original L, and also phi is in these Fs. Just for the sake of time, I am going to completely gloss over a very minor detail, and that is that I want certain things to be Borel, and I only know certain things are analytic and maybe not Borel. But this is easily fixed. It's like small technicality, right? These might not be Borel anymore, but there is a way to extend them to make them Borel with having the same property. So that's not too. Let's not get too focused on that. Okay, and now what can we say about these sets? So these sets are tiny, and like I said, there's a way to make them Borel if you fix it. Tiny Borel sets, and they are Borel where? Well, I am taking a copy of this, right, inside the set. So they should be Borel in LNCG, which by the comment encircled in green just happens to be the same as L. Actually, this one should be D, and then this is C, right? Because that's what we want. So these happen to be tiny Borel sets. And what do we do now? Okay, so now comes the trick. Okay, let's use this. Yeah. If I manage to prove this, I'm almost done. Because I have convinced you that if you start with a large set of copies, then you can always find a set of the copies of the next graph that is still large. So you can recursively do this over and over again, and whatever limit that will be a graph with Borel chromatic number 3 because of the property 1, and that one is the graph that I will call L0, right? Okay, so now consider, so here's the trick. We consider L minus, which is simply you remove from L all the graphs, all the sets of the form HMD, right? So I remove all of them because these HMD are tiny in the same space that L is large in. That's the trick. So you take all the D, all the M. Now this is the part that, like, again, I said people will not like at all. So D comes from an uncountable set, but not really, right? So D is only extending C in one coordinate. So this is a countable union if you maybe fix the notation a little bit, right? So DMD is large because you're removing from a large set, so all in the same space, right? That's the thing that was kind of problematic. So this is a large set, and you're removing a countable union of tiny sets. So this is surely small, and then that has to still be large. But then we're done, because now you can do what we did before, right? So by 2, there must be some extension where the next stage of construction of this is large. Sorry, non-empty, right? So there exists phi such that phi is inside ln plus 1 for this particular parameter g, and this will cause a contradiction, right? Right. So then if you take phi I, then this will be inside the H set based on my definition. Sorry, I skipped a step. That's why it doesn't make sense. Okay, so far we haven't done anything, right? I just used 2 to produce some copy of this large set. Sorry, some copy inside this set. So phi is actually in L plus D now, right? Right. But what did I start with? So somewhere here, I assumed that this was a union of things, right? Oh, up there. Right, so L plus D is a union of those things, right? So phi must be in one of those. So FMD for some M, right? And then this will produce a contradiction, right? So basically what you do is you conclude that phi, I have to pick the right endpoint again. Phi I will be an element of this with L minus. Now where's the correct endpoint? Okay, so phi is in this set. That means that phi evaluated at the endpoint is in this set with the endpoint attached to it, right? But that is just the definition of the set HMD. So phi I is inside this thing where you have to pick the right endpoint, right? But it is also an element of L minus, right? Because that's how we pick these things. Sorry, I should have written that one there, right? That's where we applied to. And these two are disjoint. These two are disjoint because somewhere on the board it says they're disjoint. I mean, right? Obviously, that's how I constructed these, right? Okay, so that's a contradiction that I got from assuming that there is no parameter whose extension will produce a large set. So this proves the lemma. And now let me just quickly tell you what LC is, because I haven't even told you what that is. So LC, I still have the parameter. I'll tell you how to get rid of it in a second. Is the graph on n cross 2 to the n, where 2 nodes are adjacent, if they are adjacent in all the copies, right? Where 2 nodes, 2 vertices. So the first parameter will describe the path position. The second parameter will tell me at what stage was the position added, right? And the third parameter is the story of the copies left, right, in which you are to be found in those things, right? So if you have 2 vertices, there's too many things here. K, I, are adjacent in C if and only if they are adjacent everywhere where they are to be found in those graphs, right? So if and only if I n of K I M I X I, how do we concretely find a vertex determined by these three parameters inside that thing? Well, it's all gone, right? Because it's too many things to write down at the same time. But the idea is that you start with the first letter, right, of the node tells you what position were you in the path when it was added. The second, coordinate will tell you what is the story, right? Actually, that's all you need. That's all you need. So this will be just x restricted to n minus m. For example, what happens if m is equal to n? Then this is 0, and all you do, you're only a path. So that tells you that you were added right there, right at the stage, right at the nth stage. What happens if m is 0? M is like the age of the node, right? So if m is 0, that means you're really, really old. I guess like the reverse of the age then. So if m is 0, you were one of the original vertices, one of the original in the very first path that was defined, and then you were copied a million times afterwards, right? If m is 0, then this is just the full story, and you were one of the original elements in the very first L0, right? That's more or less the idea. So these nodes are adjacent. Adjacent in all ln lnc, right? Yeah, okay. I still have the parameter c for all n. And when does this make sense? Well, n has to be bigger than m, right? You cannot, if you think about it, otherwise this doesn't make sense, right? Okay, so that's how L0 is defined. The property 1 is used to show with a bare type argument that L0 has Borel chromatic number at most 3. The argument that I already erased, that the fact that L0, all the nodes have degree at most 2, tells you that the Borel chromatic number is at most 3. So the Borel chromatic number of this is actually exactly 3. Let me try to see if we can write down the last few seconds of the proof. So to be honest, the rest of the proof is just we already did all of the hard work, right? Now it's just writing and using all these things in the right order. So remark, the Borel chromatic number of LC is always 3. Now, something that I will obviously not have time to prove, but I can just quickly mention. This is a theorem in the original paper, the 2021 paper that I mentioned at the beginning. These LCs are all equivalent to each other, right? So if C is unbounded, if C, let's say CD, are unbounded and only take odd values, then LC embeds continuously into LD, right? So there exists an F continuous homomorphism. So these are all equivalent, so you can just pick your favorite C, and since all of these will be equivalent, the conclusion of the theorem holds for whatever LC is simplest, right? What value of C is simplest? Well, you can just pick all the odd numbers in order, for example, right? That works. Okay, so what's the what's the actual proof of this? So suppose we already did almost everything, right? So suppose that you have a graph with Borel chromatic number bigger than 2. And then by one of the lemmas that I wrote down, this set is large, right? I think I wrote it in the contrapositive. If this is small, then this is at most 2 because you can do that. So recursively find ln inside home ln c. Yeah. Recursively construct. So like I said, this is the problem, right? You have to update the pesky C all the time throughout the. Yeah, I mean, construct C and ln large for L such that the following happens. So first, whenever I extend this construction to the next stage, this is compatible with the previous stage. Sorry, with the previous copies, right? So this should be ln plus 1. No, this should be just ln. ln plus 1. Yeah, I think now it makes sense, right? This is compatible with the previous copies. Wait, is that what I want to write? Sorry, just a second. Yeah, of course. That looks so weird to me. Right, so ln plus 1, the next stage is simply a large set contained in this one. This is the one that you can actually construct, right? So this is n. Now here are 2 conditions that you need for the mapping to be continuous. You want the large sets to shrink in size so that they determine a unique point inside the space. But this is actually not too difficult to achieve with all the thing we've done, right? So for all vertices, sorry, I keep forgetting to write vertices. If you take L Ln and you look at the copies of U, and then you take like the closure and the diameter of the set so that it's well defined. This is all a polar space, right? This is a subset of X, the vertices of G. So surely there's a way to measure the diameter so that it's compatible with the topology and will actually produce a continuous mapping, right? At the end. So we want the diameters to shrink. And this is not too difficult to achieve, right? Because if this didn't happen, you can just take your large set and split it into countably many pieces that are small, with small diameter, and then one of them is large, and then you pick that one, right? So this isn't too much to ask for, since we already proved that these are large sets. Right. So I think I ran out of time to define the actual mapping. I mean, I can just write down the mapping, right? So this is older. I want that drawing though. So let me erase this part. Right. So what is the mapping, right? We wanted a continuous homomorphism that makes everything work. So the way you make this work is that you define f on kmx as follows. So you will basically take the intersection of these shrinking sets, which by compactness will give you a unique point. Maybe I should write it like this to be extra formal. And you want the sets that shrink. Let me just copy this so I get the right indices, because there's no time for mistakes anymore. Right, so this is just L N I N M K X. Right? As you increase the value of n, you find smaller and smaller sets that correspond to larger and larger copies of these things. Right? So hopefully that makes sense. Okay, so this then F is a homomorphism from n homomorphism from LC to G. And then you apply the theorem that says that, well, instead of LC, you could have just picked one of them because they are all equivalent, right? So just pick whichever one is easiest and call that one L0. And I think that's all we have time for.